Hey, good morning, everybody. How's everybody doing? This quick lesson is just looking at growth rate and a little bit of age structure, but more about growth rate. Growth rate is really what we use to determine the population growth, how fast it is increasing or decreasing. Age structure is just, how that population is structured. Are there more young individuals, more old individuals? Is it evenly distributed, and so forth? So let's get into this. Population growth. When we look at population growth, populations in ideal circumstances will grow in what would be considered like an exponential growth pattern. Exponential growth means that 1 becomes 2, 2 becomes 4, 4 becomes 8, and just keeps growing exponentially. Now, with this, there needs to be ideal circumstances, right? In order to have this exponential growth, in order for this population to keep increasing in size, there needs to be this vast amount or unlimited supply of resources, right? Food, water, space, right? And there's no predators. There's no downward pressure on the growth of this population. As you can probably tell right now, exponential growth can't happen forever, right? It only happens for short periods of time under ideal situations. Exponential growth can happen both on a short time scale and long time scales, right? So you can picture exponential growth of insects. All of a sudden, the population is flooded with insects, right? You can picture bacteria, exponential growth of bacteria. I take a bacteria, I put it on a petri dish, right, which is just a dish to grow bacteria, and you're going to get exponential growth of that bacteria until it floods that petri dish, right? All that can happen in a matter of minutes, matter of hours, definitely a couple of days. But exponential growth can also happen over years and years and years, right? Elephant populations could be growing exponentially. However, the growth rate of elephant populations are fairly slow. They only have offspring every year, every few years. So therefore, they're growing exponentially, but that rate of exponential growth is much slower with that population. So exponential growth doesn't always mean like a matter of minutes. It could be exponential growth over long periods of time. And as we said, no population can exhibit exponential growth forever. Okay. So what happens as that population is undergoing exponential growth, you start to get those limitations that come into play. You start to get the limitations of resources, the limitations of predation, the limitations of space. And what's going to happen is you're going to kind of see here initially, we see this growth, this exponential growth initially, but then you're going to start to see this downward pressure on the population. So it's still growing, but the curve is flattening out. So the rate of growth has decreased. And now the rate of growth is kind of flat, kind of maintaining that population. So when we look at this, what happens in most populations is they transition from an initial exponential growth, they transition to what's considered a logistical model, logistical growth. And when we look at this, we can really break this down into 3 major phases, right? Here's the carrying capacity. Here's the phase 1. So population grows rapidly. So basically exponential growth. Phase 2 is when you get a slowing in that growth, but that growth rate is still increasing. It's just slowing, but it's still increasing. And then phase 3 is when that growth rate has stabilized. So it's really just maintaining at this point. What we call that point where the population stabilized, we call that carrying capacity. Carrying capacity can be noted as K, which I'll show you in a second. And it's just basically the number of individuals that ecosystem can support, right? If you look at Central Park can only support so many squirrels. There's a certain carrying capacity, amount of space, resources for squirrels in Central Park. If we have a very lush ecosystem in terms of maybe we had a winter with a lot of snow, we had a lot of rain, sun coming into the spring. So there's this enormous amount of growth with the organisms, the plants, the trees, the grass in Central Park, right? There's more resources. You could see that the carrying capacity for squirrels in Central Park might go up just a little bit because of the environmental factors have changed. So the environment, so the resources available environment is really what dictates carrying capacity, or the main thing that dictates carrying capacity. So as we kind of stated, there's really 2 models of growth. There's that exponential growth, right, which is in ideal situations with no downward pressure. Again, that can't happen forever, only happens for short periods of time. Then there's the logistical growth, right? So there's been this restriction. We had exponential initially. All of a sudden, there's the downward pressure from the carrying capacity on this population, which slows the growth rate to even out or to come to some type of dynamic equilibrium around carrying capacity. And then if you kind of look at this, to give names to it, sometimes we call this the J curve, and we call this the S curve because it curves like an S. Okay. Now with this, it's a good time to kind of talk about different organisms have different strategies of population growth. And they have different kind of reproductive strategies. So you don't need to know the equation for population growth, but this is the equation for population growth. So change in n, so delta, it means change. So change in n, kind of like a derivative if you're doing calculus, over changes t. So the size of the population over time is your population growth. Now what determines that is the R max value. So this R right here, this is determining the growth rate or the growth ability of that organism, that species. Some organisms have a ton of young. So if you think of insects where a spider or another insect can have hundreds of offspring, they have a very, very high R max value. If you think of elephants, they have a very, very low R max value. So number of offspring they put into the environment when they reproduce. Okay, so that's what this R max value is. This K in this part of the equation here is really kind of the downward pressure of the carrying capacity. So this is a positive factor in the growth rate. This right here is the negative factor, the downward pressure in the growth rate, and that's a K right there. Okay. The only reason why I'm showing you this is because when we talk about reproductive strategies, some organisms are classified as R strategists. Some organisms are classified as K strategists. So if you have an R strategist organisms, right, that R comes from the idea that they are really kind of focused on that R max value. So they're really focused on that reproductive value, lots of organisms, lots of offspring. If you have an organism as a K strategist, they're not focused so much on the R max value. They have lower R max values. They're focused more on kind of the carrying capacity, really maintaining around that carrying capacity. And there's a whole range of organisms from R to K strategists. So we're going to focus on organisms that are clearly, an R, clearly a K. So R strategists, right? Oysters, insects, organisms that flood the environment with many, many, many offspring. Are R strategists. So they have many offspring. The young are typically small. Oysters don't really take care of their kids, right? If you have hundreds of offspring, there's no parenting going on there. They tend to mature quickly, right? Which means they tend to mature and able to reproduce. And typically once they reproduce, they die off. They only reproduce once. So insects are great examples of R strategists. They really maximize flooding the environment with as many organisms as they can. The ones that survive, survive. The ones that don't. And that's kind of how they undergo their reproductive success. K strategist is the opposite. So chimpanzees or mammals, for the most part, are more K strategists. They typically have fewer young, and there's a lot of parenting going on. They take care of their young. They try to, because they only have so many offspring, they try to ensure that those offspring are going to reach reproductive age. There's a lot of parenting. There's slow maturation. It takes a while for them to reach reproductive age. But once they reach reproductive age, they reproduce a number of times. They don't just have one litter or one round of offspring. They can have numerous rounds of offspring. Again, mammals are great examples of this. Again, it's always black and white. There's always gray. So you can kind of see there's this transition from R to K strategists, which is a nice kind of image down here to see that. Okay. The one last thing with this is just talk about factors that actually limit the population growth. So what factors kind of play a role with that K part, the carrying capacity of the equation? These are limiting factors. So what can limit factors? Well, we have competition, we have predation, parasitism, disease, weather patterns, natural disasters. All these are different factors that can limit population size. We really group them in two terms. We group them in density-dependent factors, and we group them in density-independent factors. I'm going to jump back in a second here. So competition, predation, parasitism, and disease, these increase. They become more intense with the density of the population, right? If I have more organisms in a given area trying to get the same resources, competition is going to increase. If the density of that population decreases, competition is going to decrease. Predation. More prey, more predators, more predation, it increases and decreases. The amount of predation increases and decreases with the density of the population. Same with parasitism and disease, right? When you think of the spread of the flu or the spread of coronavirus, right, you're going to have more spread in areas where people are close to get together, hence social distancing. That's what people are trying to do these days. So density of a population plays a role there. Natural disasters, unusual weather, like human disturbances, things like that, they're not really dependent upon density at all. If a hurricane comes and wipes out the shoreline, it doesn't matter if it was densely or scarcely populated. So these are density independent factors. So kind of going through those for you. Here we go. So here are density dependent factors. So these are limiting factors that operate strongly when population density is high. So disease, competition, predators, herbivores or herbivory, parasites, crowding, human impact. All of these are density dependent factors, right? The more densely populated, the more factors going to be. Density independent factors, these are factors that really don't care about the density of the population. So volcanic eruptions, temperature, storms, floods, droughts, right? The major environmental disasters, pesticides, major habitat disruptions such as right, the flooding of New Orleans, or just the growth of a new condominium complex, on some undeveloped land. All of those are density independent factors. So hopefully that helps you kind of understand this today. If you have any questions, we can talk about it next class. And thanks for listening.